Hi, good morning all. I will start the lecture now. Very good morning, everyone. Am I audible?
Yes, yes. Good morning. Yeah,
Morning,
you
ma'am.
can start. I think people will join, and
Okay, ma'am.
Veena ma'am will join only in the evening. I think she has some.
Okay, ma'am. No problem, ma'am.
But I think you can start.
Okay, ma'am. Sure. Okay. So as of now, is there any doubt with the sessions which we discussed yesterday, or any clarifications needed?
No, ma'am, no doubts.
Okay. Okay. Thank you. Okay, now yesterday we have completed till the history of quantum computing, right? Today now we will directly start with the Moore's law. Moore's law is what do you know about the Moore's law? We have already studied about Moore's law in our school. Can you just say and explain it? What is it? I want to have a conversation with you all.
Like there is a particular limit until where we can like keep expanding the number of resistors, the
Yeah,
number of transistors in a
yeah,
chip. I think.
yeah. You're absolutely right. Moore's law is nothing but in every 2 years the software making I mean the chip making company can reduce the size of the transistors so that you can accommodate more and more transistors inside the chip. Because if there is more and more transistors, if you keep on updating, if you increase the number of transistors in a chip now, the complexity and the problem solving capacity of the computer increases a lot more. So why this Moore's law is so famous in the classical computing. But does it apply to the quantum computing? Answer is no. Why? You can ask me why. Because we in quantum computing we are dealing with the subatomic stage.
Hello,
We are hello.
hello. Sorry, Shalini. Sorry to interrupt.
Okay.
But your screen is not shared.
Okay. 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 Oh yes. Okay. Is my screen visible now?
Yeah, yeah.
Uh-huh.
Now it's visible. Yeah.
Okay. Yeah. So thank you, sir.
Welcome.
And so this is Moore's law. And do you think that Moore's law is applicable to the quantum computing? No, because Moore's law is designed only for the classical processors. I mean, for the conventional processors. We use Intel and i3, i-core, all these things. For all these processors only, we use Moore's law. Moore's law is applicable only to till that stage. The one person has rightly mentioned you have a certain limit only to reduce the size of a transistor. You can't do more than that. That is another point. But the main important point why Moore's law is not applicable in quantum is we're dealing with the subatomic stage. We're dealing with the electrons. But this is not the case in the classical computing, right? So that is the main reason why Moore's law is not applicable in quantum computing. We are going beyond the Moore's law. You can say like that. We are going beyond the Moore's law, and there are some news also available. We will discuss in the upcoming slides. What are the like some companies have started making the chips exclusively for quantum computers. We will discuss this in the upcoming slides. I've included even that. Okay, and yesterday one gentleman has asked whether the base, I mean, whether the concept lies the same for classical computing and quantum computing, whether these things are same. I said yes. Now you can see that uh, bits same concept applies in the classical also in the quantum also. In bits in quant you are in the main differences in that you use classical bits where it is only either 0 or 1, but in quantum it is in the superposition state. Okay, so we will discuss the same in the same way. I will come to the slide after explaining all these bits and gates, so that you will understand the flow. But the concept lies the same. This is how quantum computer works. This is the same flowchart I gave for classical also. Now it is quantum bits. The main difference between classical and quantum is, in classical I mentioned that it is 0 or 1. 0 or 1, it's either or. Okay, but in quantum it is in the superposition state of 0 and 1 both at the same time. I hope you remember that yesterday I mentioned about the light in the original state is in the superposition of wave and particle. When it interacts with the matter only, it collapses to either one of these state. It becomes wave in Young's, and it becomes a particle in the photoelectric effect. We have discussed right yesterday. The same concept applies with the quantum bits also. Okay, so in the original state, it is in the superposition only, 0 and 1, both at the same time. Only when it interacts, it collapses to either one of the state. Either it is 0 state or 1 state. Okay, so now I hope you know the importance of going through the light and the concept which we have discussed yesterday. This is the reason why I mentioned of these concepts yesterday. Now I hope you can able to relate. Okay, so we can say, so 0 and 1 are the base state. We can for in bits, in classical bits now we don't have to represent in Kate or Bra notation. It is just 0 or 1. But this is not the case with quantum bits. Okay, we represent it. We have a separate notation to represent 0 or 1. That notation is called as bracket notation. Yeah, Brahman's row, we represent it in the row form, and Kate means it is in the column form. Okay, now we have in the below slide, now we have shown this 0 and 1 is in the Kate notation. We will discuss this more in the next slide. The bracket notation is also called as Dirac notation. We have two names, you can say, either it is bracket notation or it is a Dirac notation. Okay, so above is a Kate notation. So this 0 and 1 is a Kate notation. Why? Okay, you can ask me, how do you find the difference between bra and Kate notation? We can discuss right now. We can discuss now. By default, we can take by default bits in the Kate notation, means in the column format we can take. Why you can ask me why you are taking in the column form, why you are taking in the Kate notation as a default form? Because it is easy to represent in the column form. That is a reason for why we are taking in the column format to represent the bits. Okay, I mean, sorry, qubits. So Bra notation I mentioned, it is rows. You can see the difference between bra and Kate notation. You have the lesser symbol to the left hand side and the straight line to the right hand side, and the Kate notation is the line to the left hand side and to the and the greater symbol in the right hand side. This is how we can find the difference, whether it is a bra notation or it is a Kate notation. For example, you take bra notation of a 0. Zero Brown notation, you can just see to the second point that lesser than symbol is to the left hand side and the straight line is to the right hand side, and then inside between those we have mentioned 0 there. That is how you need to notate. That's how you should represent a qubit. That this is the exact notation of a qubit. You can't do it in the classical. This you can do only in the quantum. This how you should notate 0 and 1. Okay, and I have mentioned brand notation as rows. Okay, so uh, one and actually this zero you can note it as 1 and 0. Like um, in the next slide, you will see 1 as 0 and 1, and 0 as 1 and 0. Means 0 you can write it as, I mean, you can represent it as 1 and 0. I hope you can try to understand what I'm coming to say. If it is 1, if it is 1, first you need to write 0. If it is 0, you need to write 1 first. You have to check whether it is row notation or column notation. If it is a row notation, for example, if it is a bar notation, and you're representing qubit 0, you need to write 1 first and then followed by 0 in the row format. Now we are representing 0 in the Kate format. Zero, gate 0 means we have to write 1 first and 0 next, in the column format. That is the difference between bra notation and Kate notation of 0. Now we can see the bra notation and Kate notation of 1. Okay, so here, as I've mentioned, 1, if you have bra 1 notation, you need to write first 0 followed by 1 in the row format. In the Kate notation, sorry, it should be Kate 1. I have wrongly mentioned it as 0. It should be Kate 1. Okay, so if it is Kate 1, you need to mention it as 0 and 1. Here I have mentioned it as 0. So why it is 1 at the first, and the second, and in the second, you have mentioned 0. If it is 1, if it is Kate 1, you should mention 0 first, followed by 1. If it is 0, then you have to mention 1 first, then you have to go to 0. This you will understand when I share these slides. I will share these slides. You will get to know more and more about what I'm saying. Okay, and 0 and 1, Kate, here in the third point, where I have noted as Kate notation. I have mentioned 0 and 1 are in the Kate notation in the column format. It's because it is easy to represent. So why? So 0 Kate 0 and Kate 1, or you can say bra notation also. You can represent in the bra notation also. But basically 0 and 1 are linearly independent, because it doesn't, because it doesn't want any other state, because it is not dependent on any other state, any other qubit state. It is originally in their own state itself. 0 and 1 are in their own state, and their SOY they are called as linearly independent. Okay, and this 0 and 1 form the basis of other states. Sorry, it should not be matrices, it should be states actually. Okay, they become uh, the basis for other state. Basis means you can use 0 1 1 to do vector addition and scalar multiplication. 0 1 1, or not in 0 1 1, you can use it in the, you can do vector addition, and then you can achieve the superposition state. This is how we can achieve a superposition state, by linear combination. Linear combination means nothing but you can do vector addition and scalar multiplication. I wanted to mention here one thing. You need to know a bit of linear algebra. You need to know what is vector addition, you need to know scalar multiplication, you need to know about the matrices also. This is bit of important in quantum computing. If you face any difficulty in learning linear algebra, we can also, you can just share. If you need any other sessions for that, we will also try to include that. If what is your opinion, you can say now. You need any other you need any sessions for linear algebra, basis of linear algebra, because this is important in quantum, for the beginners. If you're not aware about, or you need to have some recall, you can also say that. We can also host a session on that, no problem. We can You can just say, discuss and say your opinion at the last, after I complete this, after we complete our discussion about this quantum. Okay, now we came to superposition principle. We have discussed Kate 0, Kate 1, bra 0, and bra 1. Okay, and 0 and 1 are the basis, because they are the main reason why superposition happens. Okay, they, with the help of them only, superposition state is achieved. Okay, um the point 2, if you look at the point 2, you can see this is Kate 1, because Kate 1 means, in the first we have mentioned 0, and next is 1, plus 1 0 means it is Kate 0. First is Kate 1 plus Kate 0. You add, and you will get, you do vector addition, and you will get 1 1. Okay, this is in the, now 1 and 1 is in the superposition state now. And you can also do scalar multiplication with this. We do this vector addition and scalar multiplication because we need to achieve the superposition state. That is the reason we are doing it. This is how quantum qubits work. I know it is a bit difficult to understand right now. But when you put your time and effort into it, you will surely understand in-depth concept about this. The above is a scalar multiplication. Scalar means like you don't have any scalar. You know the difference between scalar and vector, right? Vector means having magnitude and direction, but scalar doesn't have. You know, I think scalar doesn't have direction. It only has magnitude. So as for scalar, vector means you represent in the you have some notation above the letter, okay, like exponential mark. But scalar doesn't have that. Scalar nothing but a simple digit. You can take it as a simple digit. Two is a scalar because it is a simple digit. It is two is in the scalar notation now, and we are multiplying that with the with the above I mean result, and we can it is in the superposition state. So this is how we achieve a superposition state, and they are now they become linearly dependent. Means why I'm saying linearly dependent, because we used 0 and 1s here to achieve that state. If you remove 0 and 1, you it becomes it doesn't survive. Superposition state can't be achieved. So why it is in the linearly dependent state right now. Next, the probability. Okay, now we have achieved the superposition state with the help of 0 1 1. You can ask what is the probability whether it is in the zeroth state or one state. This is a generic superposition state. Okay, Kate's this notation is Kate psi. Kate psi is in the superposition state, and alpha and beta are the coefficients of Kate 0 and Kate 1. For example, you can also say it is the strength of the whether how much strength that state has. This is the generic notation of the superposition state. So probability of Kate 0 is you have to take the absolute, you have to take the coefficient of the Kate 0 and then you have to square it. You will, and then you have to take the probability of Kate 1. You will get the I mean you have to square the coefficients of Kate 0 and Kate 1. That must be equal to 1. Okay, because probability must be equal to 1, right? we have we have studied in our schools and colleges in the first year also. Probability should be equal to 1. This is a generic notation of the superposition state. I mean here alpha and beta is the coefficients. I'm just taking it in a generic form. Alpha square modulus of alpha squared and beta square should be equal to 1. This is how superposition state should be, probability should be. Next is the next most important concept is quantum entanglement. In entanglement you have two bits usually, because for example, if one qubit I'm keeping it in earth, another qubit I'm keeping it in Mars, they both know each other. If you measure the value of a qubit, if you know the properties of that particular qubit in earth, you can easily understand the properties of that particular qubit in the Mars. This is how entanglement works. You, for example, if you know the state, if you know the qubit state in the earth, you can measure the qubit state in the Mars. That is the meaning of entanglement. You need to achieve the superposition state to get that entangled state. You can't so the first step of achieving the entangled state is you should be in the superposition state. Not all the superposition qubits can achieve the entangled states, but some qubits can achieve entangled state. You can ask why only some, why few or not. The research is still going on, and they are yet to find why qubits are getting in entangled state. Even we don't know the answer for that right now. The researchers are working on that, why entanglement is happening. So, answer to your question, why can't we know why these qubits are in the entangled state? The answer is even the researchers are trying to find out why qubits are getting in entangled state. Okay. So I mentioned that for entangled state you need two qubits. Okay. And this Kate psi is in the entangled state, and root 0.5 is the coefficient of 0 Kate, and 0.5 is the coefficient for 1 Kate 1 1 state. Okay, and if you take the probability I mean, of 0 0 state, it becomes 50%. In the generic state I've mentioned, you have to take the square of the coefficient alpha square. The same way, you need to take the square, you get 50%. And in for the kate 1 1 state, you need to take the square root of the coefficient, you will get 50%. So there's a 50-50 chance that it is in the it is in the state of 0 0 or 1 1. Okay. Why I'm mentioning this probability is, earlier in the start of this session I have mentioned, uh, it is light is originally in the superposition state of wave and particle. Okay, the same concept applies here. It is in the superposition state of 0 0 also. It is in the superposition state of 1 1 also. When we take measurements, it collapses to either one of these states. Either it can be in the Kate 0 0 state, or it can be in the or it can collapse to 1 1 state also. So why I'm saying the probability as 50-50%. When you measure that state now, you will come to know whether it is in the kit 0 0 state or kit 1 1 state. The probability is 50%, and a probability of being probability of 0 0 is 50%, probability of 1 1 kit 1 1 is 50% when you measure it. I know you find it a little bit difficult to try to understand this. This is how the quantum is, because these things we are not seeing it, these things we are not measuring it right now. No, we are not in the lab to measure whether the state is in this state, or whether this qubit is in this state, zero state or one state. We're just trying to visualize. Another thing which I wanted to say is, in quantum computing you need to visualize at the beginning stage. You need to imagine this is how a qubit is. So why yesterday I mentioned qubit, if you say one qubit it means one electron. If you say two qubit it means two electrons. You need to visualize. Visualization works here. So why quantum is bit difficult at the starting till you understand. When you understand and when you can able to visualize the concepts, it becomes very easy. I'm also in the same stage, but now I'm going to the advanced stage of this quantum, so I could able to say all these by my own intuition. To visualize, visualization is very important, right, in quantum. Otherwise you can't you will find it a bit tedious to understand. So why I'm repeating this, visualization is important. Okay, now coming back to the another important concept, quantum interference. Interference, like it is the same as this is the same concept we studied in the Young's double slit experiment. In Young's double slit experiment, what we have mentioned, that light behaves as a wave nature, right? The two wave interacts with each other, and it either forms as a constructive interference or destructive interference. The same concept applies for the quantum interference also. They can either cancel each other. Cancel each other means it is destructive interference. They can amplify each other means it is constructive interference. The same concept applies as of now as in the quantum also. So why studying that concept is important? You can able to relate it, right? Yesterday's concept you can relate it with the quantum. That is the reason why we have to overlap these subjects and work on. Coming to the third point, superposition state, entanglement, and interference, along with 2 to the power n state, makes a quantum computer to work more faster. The main difference between classical computers and quantum computer is, classical computer won't achieve superposition state at any cost because it is not working in the subatomic particle, and quantum computer works in the subatomic particle. So why it can achieve the superposition state. Achieving the superposition state is the main reason why quantum computer works more and more faster. This is one of the advantages of a quantum computer. We will come to the advantages in the later part of this slide. Now we can go to the qubit state. I mentioned 2 to the power n state. Now this is how this is how the qubit state will be. If you take one qubit, it can be in the superposition state of either 0, or it can be the superposition state of 0 1 1. Only when we start measuring that qubit state, it collapses to the either 0 or 1, like the same concept what we read yesterday, what we discussed yesterday. Light in the original form is in the superposition state of wave and particle. When it interacts with the matter, it collapses to either wave or a particle. The same thing applies here. When you use one qubit, it is in the superposition state of either 0 or 1. When you measure that qubit state, it collapses to either 0 state or 1 state. The same concept applies here. You can interrelate with now. Now we are using 2 qubit. 2 qubit means it is in 4 states. Okay, 2 to the power n. This is 2 to the power n. For example, here I have 1 qubit, so you can use, so that you can visualize as 2 to the power 1. So 2 to the power 1 is 2. If you use 2 qubits, 2 to the power 2 becomes 4. This 2 to the power n state I measured in this slide, in the third point of the quantum interference. 2 to the power n. Okay, so 2 to the power 2 becomes 4, and this is 3 qubit. 3 means 2 to the power 3 is, it is in the 8 states. 2 to the now you have 4 qubits. 4 qubits means 2 to the power 4 becomes 16. So we can come back to the 2 qubit state. In When we take 2 qubit, it is in 4, the superposition, it is in the 4 superposition, it is in the 4 states. Okay, 4 superposition states. It is in gate 00, gate 01, gate 10, or gate 11. Okay, so now if you measure that state, it either collapses to either one of the states. And the same concept applies to qubit 3 also, qubit 4 also. I hope this is clear. Now now you have superconducting trapped ions, diamond envy centers, and photonics. These are the one of the ways to make qubits in the lab. You need to make a qubit, right? That qubit can be made by one of these methods only, depending upon the applications. Photonics use light, and superconducting state you have different concept, and trapped ions you have atomic physics included in that. So qubits, mm, or task specific. Okay, so that is the point I mentioned in the fourth point in the slide. You have to The qubits are different for different purposes. For example, if you use photonics and make a qubit, it is used for that specific purposes only. So every quantum computer has qubits, and that qubits are task specific. Task specific means it is made for the specific application purposes. Okay, so why different qubits form different quantum computers. One particular quantum computer is made of qubits, and that qubit is made for particular specific application. This qubit cannot be used in another quantum computer. It is so why I mentioned it as task specific. But in classical computing, all the classical computers implements the bits in the same way. You can use the same bits in other classical computers also. The method is same for all the all the classical computers, but in quantum computing you don't have a specific way to standardize how that qubit should process. This is the basic difference between classical and quantum computing. In quantum computers you have a separate set of, you have to make qubits separately. It's like a, you can treat them qubits as a special child. Okay, every qubit has a specific purposes to application to perform. So why we have different methods and ways to make a qubit in a lab. This superconducting trapped ions, diamond envy centers, and photonics, or one among the ways to make. You can make qubit in photonics also, in trapped ions also, but they are task specific. I wanted to mention this. Okay, and now we have completed quantum bits. We are going to the quantum gates. These we don't have You don't have to do study a lot of things about this as of now. We will discuss this in the upcoming classes. As of now, we can just say the quantum gates as poly X gate, poly Y gate. In in the classical computers, we have AND gate, NOT gate, NOR gate. In the same way, for the quantum gates, you have poly X gate, poly Y gate, Z gate, Adamant gate, phase, CC NOT gates. When you go to, when you advance the topics, the quantum, the qubits increases, so the representation in the matrices also increases. We don't have to worry too much about these gates right of as of now. We just know there is, if someone asks you what are the quantum gates, you can be in the position to reply that poly X gate, poly Y gate, poly Z gates are the quantum gates. As of now, we just know these are the quantum gates. And now we are moving to the quantum circuits. So earlier we saw qubits. The qubits acts on the gates, and the gates uses the qubits, manipulates the qubits according to its according to the gates. For example, in the X gate, it is different. In the X gate, poly X gate behaves like a NOT gate actually. So if you give 0, you will get 1. If you give 1, becomes 0. It is complementary. So poly X gate uses the qubit and manipulates them according to the gates. Okay. And hundreds of millions of gates forms a circuit. This is the same concept in the classical computing also. This is same in the quantum also. Okay. So so hundreds and millions of gates form a quantum circuit, but as of now, we are in the count of hundreds. Count of hundreds means we have only till now IBM has achieved only 433 qubit stage only. They have only processed 433 qubits till now. So why? If you have only 433 qubits, you can make gates according to that only. If you make gates according to 433 qubits, and the circuit will also be in the hundred stage only. So why I mentioned it as counts of hundreds. In order to achieve millions and you have to, in order to achieve that millions of gates, we need to achieve millions of qubits. Only then you will get millions of gates. Only if you get millions of gates, you get millions of transistors in that circuits. This is the basic quantum gate. Okay, this is just a normal gate. You just understand this is how a gate looks like. This is how a quantum circuit looks like. Sorry, this is how a quantum basic quantum circuit looks like. Okay, and 000 means they are qubits, and this yellow boxes are gates. H is Adamant gate. H we have seen in the quantum gates, you have H belongs to Adamant gate. This Adamant gate is very important to achieve the superposition state. You will learn about this in detail in the upcoming classes. As of now, you just understand that H belongs to Adamant gate, and here X is Pauli X gate. It X gate is used in the X gate is equal to the NOT gate in the quantum in the classical computer. It is complementary in nature. Okay. So the blue box is qubits and the yellow box are gates. And this plus sign which you see now next to the H gate is nothing but you are doing computation with the 0 and 1. Yes, I want to mention this. In the quantum computing, the qubits start from 0. So the first gate 0 now, that is 0. Second is qubit 1. Third line is qubit 2. So you have three qubits as of now, but but the indexing starts from 0, like we use in the Python coding, right? The Python coding indexing start from 0. The same way the qubits also start from 0 only. So we have 3 qubits as of now, and it starts from 0. Next is 1, next is 2. So 0, 1, 2. These are the 3 qubits states. And beside that Admart gate, you have some plus kind of thing, and surrounded by circle. It is nothing but you're doing computation between qubit 0 state and qubit 1. That is how they measure it. That is how it works. Actually, there is a particular um, library for quantum that is called as Qiskit. This you will know when you install Qiskit in your local machines. Okay, there's a particular session for that also. Of do you import the library? Qiskit is nothing but a library. You will import that library in your own, in a local machine, Jupyter notebook, and you will make computations according to that. So you will come to know much about this in detail in the upcoming classes. As of now, we just know this, that this is a gate, this is a circuit. We have qubits and gates here. Yes. So we will discuss about the chips, not the chips which we eat, but the quantum chips. Okay, when you say about, when I mentioned about the Moore's law, in Moore's law, Moore's law doesn't apply to the quantum computing, quantum computers, because Moore's law is made only for the specific classical processors only. You need to make a separate chip for quantum computers to work. This is completely oriented to the quantum hardware. We don't have to go in depth, but this is a news. This Ion Q is a company. They have made a new glass quantum computer chip, and IBM also has released a roadmap. They will plan to make 1,000 qubit chip by 2023. Okay, so the chips, you just understand that Moore's law doesn't apply to the quantum computers, so you need to create a separate chip. So these companies are taking initiatives, and they are making quantum chips to make the quantum hardware. Why we are discussing about the chips means, because we need to create a quantum hardware. Only in quantum hardware we can dump the algorithms inside it, and then we can work according to the specific application. Now we come to the quantum algorithm part. And these are the algorithms. In classical computing, you have linear search, sorting, tree. All these are algorithms in the classical computing. In quantum, it is Dutes, Joseph, Bernstein, Vazirani, Simons, Shores, and Crovers. All these are the algorithms. These algorithms we dump in the circuits to run for the specific applications. What are the applications? Teleportations, Teleportation, finance, chemistry, machine learning, optimization, and in mathematics also we use quantum applications. Okay, now I'll come back to the first slide. So do you understand? Can you able to make a flow of the all the concepts I've said now right now? Bits, it's in the superposition state of either whatever the qubit we give. For example, if we give take for example, you take one qubit, it is in the two, it is in superposition of two states. Okay, it is in either 0 or 1, and that qubits is utilized by the gates, and it is manipulated according to the gates. For example, if you use poly X gate, it is nothing but a NOT gate in classical computing. So you can perform so the bits are manipulated by the gates, and hundreds of millions of gates form the circuits. And then you're using the algorithms, Jude's Josa algorithm, Shor's algorithm, Grover's algorithm in the circuits, and and uh, and we are making the specific application depending upon the algorithms which you are using. Every algorithm has like different set of specific orientation. Okay, specific task oriented. So depending upon the algorithm, the application also changes. Okay, this is the flow of quantum computing. This is the same with classical computing even. Okay, till now, is there any doubt or anything, any clarification needed? I know it's a bit difficult to understand at first, but we can learn it gradually.
Fine.
Is it okay? Everything is fine, right? Any doubts? Okay. I will assume that there is no doubts as of now. I will go to the advantages of quantum computing. What are the advantages? Like, quantum computing is completely different from classical because of the three important concepts: superposition, entanglement, and quantum interference. The main reason why quantum computers are more faster because of this, because it achieves the superposition state. Next, it is 2 to the power n, it because it achieves 2 to the power n state. For example, you give one, if you take one qubit, it can achieve 2 to the power 1, means it will be in the two states, two quantum states, two two states, 0 or 1. If you take 2 qubits, it can be in 4 states. If you take 3 qubits, it can be in 8 states. If you take 4 qubits, it can be in the 16, it can be in 16 states. So this is the reason why quantum computers work faster, because of the superposition state. Also, when you include more and more qubits, you can solve more problems, and you can and you can solve more complex simulations also. For example, the teleportation has not been into the picture right now, right till now. But if you add more and more qubits, for example, if you cross more than 1,000 qubits, if you include 2,000 qubits, you can try to achieve. You can try to work on quantum chemistry, because quantum chemistry is the molecule we discussed about atoms and molecules in chemistry. Okay, you can understand more and more if you include more and more qubits. More and more qubits equal to, you would go in depth of the particular. For example, you're taking quantum chemistry. If you have more than 2,000, 3,000 qubit quantum computer, you can go to the base molecular level of the atomic state. Okay, that is the main reason why we need to include more and more qubits. So these are the advantages of quantum computing. First is it can achieve superposition state. If it achieves superposition state, the quantum computer works more faster, and it gives more accurate results, and you can solve more complex problems. The main drawbacks of the quantum is hardware is difficult to construct. Why I'm saying hardware is difficult to construct is you need to create a separate chip. Why can't we use the chip in the class as it is used in the classical computers? You can't use it because Moore's law doesn't support it. You have to go beyond the Moore's law. So why you have to create a separate chip for the quantum computers in itself, and you have to work on that. You have to include more and more qubits. That chip must have the capacity to include more and more qubits. So why quantum computer is bit difficult to construct. It takes a lot of manual effort, and the billions of dollars must be invested in making a simple quantum hardware. And error rates, there even if you consider, even if you make a quantum hardware, you can't be so much accurate in result. You can have error while performing quantum computation. That is one of the major problem in quantum computers. Researchers are working on that. Till now we didn't get a proper solution for that. Researchers are working on that, and they are task specific. As I already mentioned, different qubits is equal to different computers. You can't use the same qubit which you use in one computer, one quantum computer, in another quantum computer. Qubit, if the qubit is specifically made for a particular quantum computer, it is only restricted to that. You can't use it for another quantum computer because of the applications, different applications. You can't for example, you can't use the qubit which is made for a quantum teleportation in quantum finance, right? That is the same that is the same concept applies here. You can't use one qubit which is made for one quantum computer to be used in another quantum computer. It is self-explanatory, no? This slide. So I don't have to we don't have to worry too much of about the drawbacks. Researchers are working on that. Now we can know what are the present scenarios going in the quantum field. IBM, we all know IBM is working more in the quantum field. So as IonQ, but IBM is prominent in the quantum field now. In 2019, they used 65 qubits. They've increased it to 127 qubits as in 2021. 2022, they have 433 qubits. In 2023, it is 1,100. They will achieve 1,121 qubits. If you achieve more qubits, you need to have more quantum volume. More quantum volume is nothing but the circuits which we are discussing. The circuit, if you have more qubits, the chips should also be capable enough to hold that qubits, right? That is what quantum volume is. So if you have more qubits, then you have more, then the capacity of the circuit should also increase. So if the capacity of the circuit increases, it solves more complex problem. It is directly proportional, and it is self-explanatory also. Till now, in 2022, they have achieved 1024 quantum value. Next is CLOPS. CLOPS means, um, for example, I mentioned earlier that if you increase qubits, you need to increase the circuit also. If you increase the number of capacity of the circuits, the speed of the quantum computing increases because you're increasing the qubits. You increase the qubits, you increase the circuit's capacity also, and if you increase the circuit capacity, the speed also increases. You measure that speed by uh, circuit layer operations per second. It is called as clocks. In 2022, we have 10K clocks till right now. In 2020, it was 200, but in 2022, we have achieved thousands of clocks, 10K clocks till now. So yes, um, this is a summary part. If we increase the qubits, we need to increase the quantum volume. If we increase the quantum volume, we can solve more complex problems. And this also depends upon the number of the circuits. If you increase the circuits, you can increase the speed, as well as the complexity of the problem solving also increases. And you can achieve high speed quantum computer. If you increase the qubits is directly proportional to increasing the circuits. When you increase the circuit capacity, you can uh, do more complex problems. We can also, the error rates also decreases. So high speed quantum computer is achieved. Okay. Um, this is that's it as of now. I hope you're clear with the concepts, basic concepts, what we have discussed right now. I will stop sharing the slide. Whatever the doubts you have, you can ask, or we can discuss about this now. Do you have any doubts? I know it's a bit difficult to understand at first, but we can go gradually. There are a lot of uh, sessions on this. I just gave a brief glimpse of what is Brad notation, what is gate notation, what is superposition state, what is entangled state, what is interference state. This is the base where you can use this to you can read more, you can do self study more, and you will come to know that you can compare our discussion along with your self study. You will understand in more detail, and you will come to know a lot more about this in detail in the upcoming classes also. My another colleague will teach in in the evening session also, so you will elaborate more on the topics. Is there any doubt?
No doubt, sir.
No doubt. Okay. Okay, fine. So what can we do now? Can we end the session, or you need to discuss anything more? Because this is the basic introduction to the quantum computing. I've given a brief glimpse of quantum as well as classical. We have discussed about the Moore's law. We have discussed about the basic physics concept, and basic physics concept is applied in the quantum. We have discussed more elaborately about the quantum. You have to following sessions you will have, where each and everything they will go deeper and deeper. We have discussed about qubits, they go more deeper about that in upcoming sessions. They will explain about each and every gate, poly X gate, poly Y gate. They will explain it more detail, how this gate is formed, how these matrices are formed. They will explain it in next 1 or 2 weeks. So as of now, this is good to go. This is a kickstart for you in a quantum field. Okay, so can we end the session? If there are no doubts for you to discuss. Hello. Okay. Yes. Someone wants to say anything?
Nothing, nothing.
Okay, ma'am. I hope everything is clear. But we will discuss more about this quantum in coming sessions. I know everyone is bit of, feeling tedious to understand. It takes some time to understand. Even I was in the same position as a beginner, but I can able to explain now. I'm in a position to explain to other people also. So if you do self study from your own side, you will learn much more. See, this quantum norm, whatever the subject it is, you need to balance the lecture as well as your own self study. If you do both parallelly, you can understand the concepts much more deeper. This is how I did. I have no one to there was no one to explain my doubts also. All these concepts I studied on my own. I got some mentorship from Sunjoy sir, but all these things I did my own self study. So I'm in a position to explain to others. So you can also do the same thing because this is universal, right? I mean, whatever I'm saying, others also say the same thing. Doing self study as well as learning from a mentor, both should be balanced to go to be an expert in that field. This is one of a tip I wanted to give. Okay, so I will end the call now. We will see in the evening class. My another colleague, Sakibul, will come and explain another concepts in the evening time. Okay, so thank you all. Thank you for your patience.
Thank you. Thank you.
Thank you, ma'am.